In this video, we're going to handle this infinite series with a cool derivative trick. Now you may be wondering why I'm showing you how to handle this series with a cool derivative trick instead of some other one, and the reason why is because this series actually can be done with a cool derivative trick, which obviously isn't a given. The trick here is going to be to start with an infinite series that's very similar in structure to the one we're trying to sum, but that's not quite the same, specifically the Taylor series expansion for sine. Now, the reason why this is useful is because it's an infinite series that isn't just similar, but one whose answer we know already, namely that it equals sine. This helps us because we can use derivatives and algebraic operations to transform the infinite series side of the equation into exactly the infinite series we're trying to sum. But because we know the value of the series that we perform those manipulations on, namely that it equals sine, we can perform those same algebraic operations and derivatives on the sine function to get what our series equals. If you're finding this a bit hard to follow, that's okay. I'm going to show you how to do it step by step. Let's begin the process, examining the Taylor expansion for the sine function and the infinite series we're trying to sum. We notice that the only difference is that in the series we're trying to sum, there's an extra factor of n squared in the numerator under the sum, whereas there isn't in the sine function. So the goal is going to be to use derivatives and algebraic manipulation to try to get that n squared to show up in the sine infinite series so that we know what operations to perform on the sine function to get what the series we're trying to sum equals. Now the first thing we might be tempted to do is take a derivative in order to bring down a factor of n. But of course the exponent on x is 2n minus 1, so it won't just bring down a factor of n. It'll also create another term, so the trick is actually to first multiply the Taylor expansion for sine by x to get this, and now we've gotten rid of that pesky minus 1 in the exponent, so now we can take a derivative to bring down a factor of n. It'll also bring down a factor of 2, of course, but that 2 doesn't matter because we could just divide it out. The fact that it brought down a factor of n is the important thing. This of course doesn't get us all the way there because we need a factor of n squared, and we can't just directly take another derivative and get it because the last derivative reintroduced the negative 1 in the exponent, which will cause the same problem that we just addressed. Of course, that means that we can solve the problem in exactly the same way. We can just multiply by x again, giving us this. With this second derivative done, we're left with exactly the same power series we started with, but with a new 4n squared in the numerator. We can divide the 4 out to the other side to get rid of it, leaving us with exactly the same power series we started with, but just an extra factor of n squared. And with that, we have successfully finished converting the Taylor series expansion of sine into exactly the power series that we wanted to sum. Specifically, we've obtained this equation, which sets the power series we wanted to evaluate equal to the derivative of x times the derivative of x times sine, and that's something we can do with simple calculus rules. Taking that first derivative with the product rule gives us this. We can then take the second derivative, which leaves us with this, and then we can simplify, and that gets us our final answer, which is really quite nice. So, if you were ever wondering what would happen if you took the Taylor series expansion of sine and stuck an extra n squared in it, it yields something that is non-obvious and arguably not that interesting, but it's definitely calculatable, and the way you calculate it is interesting. And that is really the point of this video. Now this trick isn't completely non-general. There are many other power series that you can handle using methods similar to this. As a result of this more general applicability than just this particular example, this kind of trick is really worth keeping in mind. Anytime you're encountering a power series that you want to sum, it's worth considering the possibility that a trick like this might work. So I hope you found this video interesting. If you did, please share it with friends, give it a thumbs up, and consider subscribing. I don't really have much else to say, so I'm basically just going to sit here until the 20-second end screen time runs out.